Welcome back. In the following sections of this lecture, we will be discussing several issues related to the receiver dynamic range. Dynamic range of a receiver is defined as the ratio between the maximum power and the minimum power. And one of the things that limit the dynamic range is the nonlinear behavior of a receiver. So before going into the details of what limits the dynamic range of a receiver, I want to make a general description of nonlinearities of a receiver for the particular case of third-order nonlinearities. Let's examine this in detail. Normally, we will make a very simple model for analyzing the nonlinear behavior. We'll make a very simple model of our components. In this model, we will treat our components as a black box having an input xt and an output y of t, right? And the dependence between x and y is the one that's graphically shown in here, right? We will have an instantaneous dependence of the output y with respect to the input x, given by this transfer curve in here. As you see, this transfer curve is a curve that's about linear at the origin, and then it limits as you increase x of t, y of t, y is limited, right? There's some amplitude limitation in the shape of this curve. When you make a Taylor series expansion of this type of curves, you end up with an expression like this, right? You have an expression in which you only have odd terms. You only have x and x cubed, no x squared, and this is because this dependence is an odd function, right? And the Taylor series expansion of odd functions only have odd terms. And because of the amplitude limiting features, the sign of the first coefficient k1 has to be opposite of the sign of the third coefficient k3, right? So here we'll assume that k1 is positive and k3 is negative. And what I will do in this section is to derive a general expression of the output y of t with respect to the input x of t for the particular case when x of t is this. There are x of t consists of the sum of two different tones, and we will analyze later on in the following sections of this lecture. We will analyze several cases: the cases in which we will only have one tone, the cases in which we'll have two simultaneous tones of equal amplitude, or two simultaneous tones in which one of them is much more powerful than the other, right? So let's see. Another consideration before switching slides. You notice that this model is very, very simple, right? We have restricted the output to a linear dependence of the input, and in practice, these things are not, receivers do not behave exactly like that. There may also be a dependence of the output on the derivative of the input, of the time derivative of the input, or also dependence of the output with the integral of the input with respect time, right? So this is a very, very simple model. This is one point I want to make. The second point I want to make is that here x and y could be voltages or they could be currents. It would be something related to the signal that this device is processing. So since the explanation is general, we will make also a general description in which we will not include dimensions, right? So we will not include units of current or voltage or something like that. So there's a dimensionless, the equations that I will use next are unitless. Now, In developing the output as a function of the input, we will use this equation that gives the general dependence of the output with respect to the input. As I said, the input, we will assume this sum of two tones, and we'll use the identities that are shown here. And the identities are the trigonometric identities for the cosine square, the trigonometric identity for cosine cube, the trigonometric identity for the product of two cosines, and the polynomial development, the polynomial expansion of the sum of the cube of the sum of two terms, right? Those are well-known equations that you know, but I put here to remind you. Now, in combining all these equations, here we have we can combine these two equations, and then when combining them, we will have in this line I have put the first order terms. In this second line, I have put the second order terms, the third order terms, the terms that depend with the cube of the with x cube. And in this line, I've put the terms that are a product of the second order terms with first order terms, right? And by using the algebraic, the equations of the previous slide, you can check that this development goes as is shown in here, right? Also, for this particular case, I've developed these terms here as these terms in here, in which we have several frequency terms for both, depending on omega 2, 2 omega 2 minus omega 1, and 2 omega 2 plus omega 2, right? So try this on your own and try to develop this equation on your own. It's simple if you use the slides from the equations from the previous slide. Now, in any case, once you reach this point, you can group all these terms in a manner that I've used in this slide. Right? In this slide, I've put all the terms depending on cosine omega 1 on a single amplitude term. Right? So this cosine of omega 1 depends on the amplitude of A1, the amplitude of A1's cube, and the amplitude of A1 times A2 squared, right? And likewise, this is done for all the possible frequency terms, right? There's a term in cosine omega 2, a term in cosine of omega 1, 2 omega 1 minus omega 2, a term 2 omega 2 minus omega 1, a term 2 omega 1 plus omega 2, and a term 2 omega 2 plus omega 1, and then other terms at the triple frequencies, right? So what I encourage you is to keep a copy of this slide, because it's this exact equation that we will later explore for the particular cases that I'm pointing out here, right? And in particular, these cases correspond to real situations that occur in receivers, which are shown in here. We will examine in the later sections of this lecture the phenomenon on gain compression, which is what happens when we only have one tone in our signal. We'll also describe what's intermodulation distortion, which happens when we have two tones of equal amplitude, and we also examine the phenomenon of receiver blockage or receiver blocking, which happens when we have an interfering signal which is much stronger than our desired signal, right? And we'll be seeing all these details in the following sections of this lecture.